Hi everyone and welcome to today's video. In this video I'm going to discuss how you determine whether or not a molecule is polar or non-polar. To do this you need to consider both whether the bonds are polar and then whether the molecules are polar. So I want to work through this. Okay, so the first thing is polar bonds. So anytime you have two atoms bonded together that have different electronegativities, then they will have different degrees of attraction for that shared pair of electrons, and therefore one atom will be slightly positive and one atom will be slightly negative. If the difference in electronegativity was really extreme, one atom could take the electron off the other, but that would then form an ionic bond. We are talking about covalent bonds when we talk about polar bonds. So within those covalent bonds where electrons are shared, then the most electronegative atom will take the greatest share of the electrons. So these electrons are still shared. Both atoms get access to them, but the most electronegative atom will have the greatest share. Now, we've talked about electronegativity previously, and obviously that ties in. But also, if you're not sure, just think, are the two atoms different? Every atom has a slightly different electronegativity to every other atom. Even if you look at a table that has Pauling values on it, and it looks like they have the same electronegativity, they will be slightly different. So you're going to assume that anytime you see two different atoms bonded together, then they will have different electronegativities. Fluorine is of course the most electronegative atom on the periodic table, so in any bond that contains fluorine, fluorine will be the most negative. Once you move away from fluorine, then you're thinking the ones that are closest to fluorine are the most electronegative. If you're about the same distance away, smaller atoms generally tend to be more electronegative than larger atoms. So oxygen and chlorine are both right next to fluorine, but oxygen is smaller, so it's going to be more electronegative. Okay. So that's the general thing on polar bonds. So when it comes to polar molecules, then you must have an overall separation of charge, positive and negative charge, within the molecule. Which means if you're thinking of like where the middle of the positive charges and where the middle of the negative charges, they have to be in a different place. So if you draw bond dipoles on all of your bonds, if the negatives are all clustered in one space and the positives are all clustered in a different space, then you're going to have a polar molecule. If the positives and the negatives coincide, then it's going to be a non-polar molecule. So the two things we need to think of are the bonds polar and are they all of the same polarity? And what is the shape of the molecule? Okay, so first off, bond polarity. So if you have a molecule that is only made of non-polar bonds, ozone is a great example on that, where you've got three oxygen molecules all joined together. All the bonds between oxygen atoms are going to be non-polar. Therefore, the molecule must be non-polar. If a molecule contains polar bonds, then it could be polar or it could be non-polar, and that's going to depend on both the shape and the types of bonds present in the molecule. Okay, so let's look at this in a little bit more detail. First thing we need to consider is the shape symmetrical or asymmetrical? A symmetrical shape is one where the bond dipoles will cancel out. And that is one where all of the bonds are evenly distributed around the central atom. So if you think even spread of bonds around that central atom, and all those bonds are identical, so they have the same dipoles, so they're between the same atoms pointing in the same direction. In that case, they can cancel out, so that's going to make it symmetrical. Asymmetrical shapes are ones that don't fit that. And actually, this slide should probably have been one further down, but that's okay. So shapes that are considered to be symmetrical include the ones that have no lone pairs. That's a really good way to think of it. There's only one exception to that. So linear shapes have no lone pairs, or if you've got, generally they have no lone pairs. They can have lone pairs, but most of them don't. Trigonal, planar, tetrahedral, trigonal, bipyramid, Square planar and octahedral shapes are the ones that are symmetrical. Now, square planar shapes have two lone pairs on them, so that is probably the exception to the lone pair rule. Shapes that are considered to be asymmetrical are bent, whether you've got one lone pair or two lone pairs, trigonal pyramid, T-shape, seesaw, and square pyramid. So all of these shapes have their own symmetry, but they're not even in all three dimensions. So if you picture, for example, a trigonal pyramid, yes, it's evenly spaced, but you've got that lone pair above, and that throws the whole thing off. So to be asymmetrical, then the bonds are not going to be evenly distributed around the central atom. There's going to be one direction, one plane, where there are no bonds, or where the bonds are different to somewhere else. That means that the bond dipoles will not be able to cancel out. And if the bond dipoles can't cancel, and that is a really key phrase, it is the bond dipoles that cancel. It's not the negativity or the electronegativity or the electrons. It is the bond dipoles. Okay, a dipole is just something with a positive and a negative end, so any polar bond has a bond dipole. Okay, so if the bond dipoles can cancel, or cannot cancel, I should say, then the molecule must be polar. So to be considered asymmetrical, a molecule must have a shape without, that's a typo there, without an even distribution of bonds, or it must have more than one type of bond in the molecule. Now, I quite like using a flowchart approach to figure this out. So here's my flowchart. So starting at the top, you've got to ask yourself, does the molecule contain polar bonds? If the answer to that question is no, there are no polar bonds, then your molecule must be nonpolar. If the answer to that question is yes and it has polar bonds, then the next thing I ask myself is the shape symmetrical? If the shape is not symmetrical, if we've got a trigonal pyramid shape or a seesaw shape or a trigonal something else shape, a square pyramid or something like that, then my molecule has to be polar. No choice. As soon as I have an asymmetrical shape, there is no choice about whether or not my molecule is polar. It must be polar. If the shape is symmetrical, so it's a tetrahedral shape or it's an octahedral shape or something like that, then the last question I'm going to be asking myself is, are all the bonds in that molecule the same? And if all the bonds are the same, then those bond dipoles will cancel out and my molecule will be nonpolar. If the bonds are different, then the bond dipoles will not cancel and the molecule will be polar. We'll have a positive and a negative end. So let's look at a couple of examples for a second. First one I want to look at, here we go, top left-hand corner, methanol. Okay, trigonal planar shape. Okay, so let's come back and have a look here. Methanol. Does the molecule contain polar bonds? Yes, it most certainly does. Carbon-oxygen bonds are polar. Carbon-hydrogen bonds are polar. So yes, it is symmetrical. So, sorry, yes, it contains polar bonds. Considering the shape is a trigonal planar shape. That is a symmetrical shape. So yes. Now we come down to the last question. Are all the bonds identical? And the answer to that question must be no. So let's just go through this again. So does it contain polar bonds? Yes, it does. Is it symmetrical? Yes, it is. It is trigonal planar. Are the bonds identical? Well, we've got carbon-oxygen bonds and we've got carbon-hydrogen bonds. So no, they are not all identical. Therefore, my molecule must be polar. So let's have a look at another one. look at SF4, okay, on the right hand side there. So sulfur, fluorine, the shape, because we've got 4 regions of negative charge around that central atom and we have 1 lone pair, then the shape is a seesaw shape. So let's come back. Does it contain polar bonds? Okay, does it contain polar bonds? Yes, it does. Is the shape symmetrical? It's a seesaw shape. It's got lone pairs in it. No, it is not symmetrical. Therefore, it must be polar. So SF4 is a polar molecule. And as soon as you see anything with a seesaw shape, a bent shape, a trigonal pyramid shape, etc., you can kind of automatically jump down to it must be polar. But good to think this through logically. Final example, PCl5, phosphorus pentachloride. 5 bonds around that central phosphorus atom. That must make it a trigonal bipyramid. So again, let's follow these questions. Does it contain polar bonds? Well, yes. Phosphorus-chlorine bonds are polar. Is the shape symmetrical? Yes, it is. Trigonal bipyramid is a symmetrical shape. All the bonds are evenly distributed around that central atom. Are all the bonds identical? Yes, they are, because we've got phosphorus-chlorine bonds. All 5 of them are the same. Therefore, my molecule is non-polar. Okay, I hope this helps you figure out whether or not a molecule is polar or non-polar. However, that does not help you answer your exam questions. So what sort of things are we looking for in an exam question or an exam answer? Well, there's 3 stages. The first step is to describe whether or not the bonds are polar based on the electronegativity difference between the atoms. So the carbon-chlorine bond is polar because there's a difference in electronegativity between carbon and chlorine. Carbon is slightly positive and chlorine is slightly negative because chlorine is more electronegative than carbon. Okay, then we state the shape of the molecule. The shape is trigonal pyramid, or it's trigonal bipyramid, or it's square planar, or whatever it happens to be. You may or may not provide a reason. It's going to depend on what the question is asking. So the last couple of years they've been wrapping together shape and polarity questions together, so you'd want to discuss the shape as well as the polarity. If you didn't have to discuss why it has a particular shape, you might just want to state the shape that it has. But that's going to depend on the question that you provided. And then you're going to figure out first, well, hopefully before you've started answering the question, you've figured out the polarity. But then you're going to state polarity and state it depending on whether or not the bond dipoles are evenly distributed around the central atom and therefore do or do not cancel out. So in other words, if we come back to that PCl5, okay, here's PCl5, have a good look at it for a sec. Here's how I go about answering a question about the polarity of phosphorus pentachloride. Okay, the bonds in phosphorus pentachloride are polar because there is a difference in electronegativity between phosphorus and chlorine. The phosphorus is slightly positive and the chlorine is slightly negative. The shape of the molecule is a trigonal bipyramid because there are 5 regions of negative charge around the central atom. Next step. Because these bonds are evenly distributed around the central phosphorus atom, the bond dipoles cancel out and the molecule is non-polar. Period. End of story. All done. Okay, that's the general approach I would use, but it is up to you now to get stuck in and practice some of these questions. Have a good look at some exam papers and have a good look at your workbooks and have a real go at these. Okay, so that's the general approach that I would use to explanations. I'll see you in the next video. Thanks very much and bye-bye.